Next will be analysis of variance. The acronym is ANOVA, A-N of variance, VA. We will divide this section into 2 weeks. So first we want to start from how to decompose our experimental data into sum of square. I just mentioned that sum of square is a quantitative number to determine what is the influence of each control factors. This is a simple data from L8. And we have 5 control factors, and we arranged control factors in column 1, 2, 4, 5, and 6. We mentioned before the arrangement of the columns to the orthogonal array will affect the confounding structure. We will talk about that later. So if we arrange this way, and this is L8 signal to noise ratio, we want to find out what is the, say, effect plot response table, right? And the response table, we first want to write out the adaptive model. We have 5 control factors. So the adaptive model will be mu plus A, B, C, D, E main effect. And the subscripts, alpha, beta, gamma, delta, W, stands for the number of level 1, 2, 3. Here we only have 2 levels. So alpha, beta, gamma, etc. will have 2 possible values, 1 or 2. From our response table, we can find out the main effects will be this way, right? Main effect will be this way. And this is the total average, 16.73, which will be the mu in the adaptive model. And this is the typical process. We did that before. Now we want to say write out or decompose this output, our adaptive model, into this graphical representation. This is L8, right? So first, 8 experiment, this bar stands for the output number. For instance, this is the first output, will be 16 something, right? Go back to the data. We have 8 output, 8 design. The first design output is 16.56. So here, the first figure here is representing output value from experimental or from the design 1 to design 8 in the L8 orthogonal array. And because we write the output using this adaptive model, so we can decompose the output into the combination of the mean, as you can see, for all the 8 design will have the same constant. This is the first constant value mean. And next will be the main effect A, B, C, D, E. So main effect A, B, C, D, E. For the first design, you can see, for the first design, here, the combination is A1, B1, C1, D1, E1. So here, A1 means in the first design, the main effect A is chosen at A1. A1, the main effect is 0.1. So here it is 0.1, a small number. B is minus 3.6. So B1 is minus, as you can see, from the average number going down, and the number will be minus 0.36. As you can see, the 0 line, the baseline is drawing from the average, okay? Average is 16 point something, right? 16.67. And this is the main effect, which means that this is the inference toward the baseline. The baseline is this number. And because in the first design, we have this combination. Each control factors will contribute their main effect into the output. So this y output, y11111, will be the summation of mu A1, B1, C1, D1, E1. Right? This is, we decompose y, the first design, into this mean and the main effect. Following the same thing for the second design. All right, for the second design, we can do the same thing for design number 2, 3, 4, 5, 6. So this is the how we decompose our output into each main effect. Simply looking at these figures, you can understand this inference of A. As you can see, effect A will change from A1 to A2. This is A1, this is A2. B, 1, 1, 2, 2, 1, 1, 2, 2. Similar for the rest. Simply look at this figure. This is similar to the effect plot. So from the figure, you can see these 8 outputs are mainly influenced by D and E, right? Because the effects are bigger. Or you can get a result directly from the response table. But simply look at this figure, you can also see D and E has a strong influence on the output. Therefore, can we use these pictures to quantify the inference? Next is we want to calculate. They are using sum of square to quantify the inference. First, we want to sum up the total sum of square. Okay, the sum of square is the output square, because each output can be written as the adaptive model like this, main effect plus the average. So this will be the adaptive model square. If we can using some manipulation, or we can expand it. Expanding will be square, 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 plus some interchange term, some AB, BC, CD, etc. And from some, because this is the main effects, so A1 and A2, the summation of A1 and A2 will be 0. So by using this property, you can simplify the square of this main effect into the summation of each main effect. All right? And this process, I skip that, but if you check the internet, you will explain why the interaction terms will vanish. Because for those interaction terms, just similar to what we did before, you can find out there will be a summation of the main effect term, and the summation of a main effect, A1 plus A2 will be 0. Similar, B1 plus B2 will be 0. So you will find out that those interaction terms will be canceled out because of the main effect properties. So this term can be simplified only the summation of the mean and also the main effect square. Here, N will represent the level of each control factor, right? N is the number of experiments, right? I'm sorry, N is the number of experiments. So N in this case will be 8 because we are using L8. So for each, we have 8 experiments. So we have Y1 to Y8. And we have 8. So this will be the total response sum of square. So all the 8 experiment total response sum square can be calculated like that. Therefore, we represent this is the total average, right? Average square and multiply by N because it is a constant, and we have N is the number of experiment in the inner array. And in this case, N is equal to 8, right? And the next one, summation of AI, we call this sum of square for A factor A. And factor A basically is the sum of square for this main effect, right? in 8 experiments, A basically only have 2 options, A1 or A2. So you can understand 4 of that will be in A1, 4 of that will be in A2, although there are total 8 experiments. Same thing for main effect B, C, D, E. 4 in level 1, 4 in level 2. We can go back to the pictures and you can see like this one, right? All the A experiment, D only have 2 selection, D1 or D2. For D1, for D2. Why? This is the property of the orthogonal array. They are symmetric and balanced. Okay, so here, this is the summation sum of square for factor A, sum of square for factor B, C, D, E. And this is a sum of square error term. Since the actual output will have some difference between the identity model value and the actual output Y. And the difference is the error. Okay, so next. This is called sum of square due to error. So we can give some name to that. First one, we call it total sum of square. What is total sum square? We move this term. This is inverse of the main effect. So we move the average to the left, and the difference between these two is called total sum of square, right? Difference from the average square, just like what we calculate for your helicopter example. This is the average, and this is the deviation from the average square. And again, from some mathematical manipulation or simplification, this can be simplified into that, which is the summation of all, sum of square summation of all the output minus total average multiplied by n. And this will be the rest. We move this term to the left, and the right part will have this. And this is called sum of square for the main effects, A to E, sum of square for the main effects. And this one is called SSE, sum of square due to error. Therefore, we can get total sum of square will be sum of square for the main effects plus sum of square due to error. All right, let's go back to the L8 orthogonal array of 5 control factors. The response will be this one, and here n is equal to 8. Since we have 8 experiments. So in this case, what is sum square due to 8? This is the term. A alpha means that A is level 1, level 2. Alpha is the number of level, right? Okay. So A, alpha is the level of A, And we have, this is 2-level design. So alpha either alpha 1, A1, or alpha 2, A2. So there are only A1 or A2. What is I? I is the number of experiments. We have 8 experiments. So here n is equal to 8. Right? However, since we only have 2 choices, alpha only have 2 choices. So here alpha is equal to 1 to P. P is the level. Here alpha is equal to 1 or 2. So P only have 2 possible selection, P alpha 1 or alpha 2. Therefore, we basically, there will be 4 cases A is set at level 1, 4 cases A is set at level 2 in a total 8 experiments. Therefore, sum of square due to A will be A1 squared, which is the main effect of A, main effect of A2, multiplied by, in these 8 experiments, A will have 4 design in A1, 4 design in A2. So 4 multiplied by this one, 4 multiplied by this one. So there will be total 8 design. This is how we calculate the sum square due to A. Actually, it's very straightforward. All right, and this is the difference main effect of A. Right, okay, I will introduce what is the degree of freedom for each experimental design, which is the how many independent variable in each variable, in each control factors or in each effects. Assume we have 3 trees. We want to find out which tree is the tallest tree, similar to in our experimental design. Control factor A might have 3 levels, A1, A2, A3. In the experimental design, in the optimum design, we want to determine which one, A1, A2, or A3, will be the optimum choice, which means that which level will give us the highest SN ratio. So our purpose is to determine which one is the highest. Then how many comparisons we need to do in order to make this decision. In this case, we only need to do 2 comparisons. We want to determine what is the difference between tree 1 and tree 2, or A1, A2. Right? And also make another comparison, A1 and A3, 2 comparisons. If we have these 2 values, we can determine which one is the biggest number, which one will be the highest output, A1, A2, A3. We don't need to compare these 2, right? We only need to do this comparison and that comparison. From these 2 numbers, we already know which one will be taller. If it is smaller, this is taller. If this is smaller, this will be taller. Therefore, for 3-level control factors, we only need to do 2 comparisons. Expand the idea, if we have n level, for instance, if we make it 4 level, A1, A2, A3, A4, and how many comparisons we need to do in order to determine which level will give us the highest output? The answer will be n-1, which will be 3 comparisons. So here, for n-level control factors, that we call it degree of freedom, will be n-1. 3 level, the degree of freedom will be 2. How about interaction? For the interaction we mentioned before, we need to determine whether these 2, in the interaction plot, whether these 2 lines are parallel or not. If they are parallel, no interaction. Not parallel, interaction. So the difference between whether they are parallel or not will determine how strong the interaction will be. This is a 2-level case, right? In the interaction plot, we have 2 lines. So what is the strength, or what is the inference of the interaction effect can be determined by the difference between these 2 lines. If this is big, interaction strong. Small, interaction small. Therefore, there will be only 1 degree of freedom, delta, in this case, for 2-level interaction. And the formula will be MA-1 multiplied by MB-1. MA and MB are the number of levels for control factor A and control factor B. For 2-level case, only 2. 2 minus 1 multiplied by 2 minus 1. So the degree of freedom will be 1. How about 3-level? We talked about that before. We can treat this 3-level interaction plot to be 2 parts. There are 1, 2, 3, 4, 5, 6 line segments. So we can determine whether between low level to middle level, they are parallel or not. We need to make 2 comparisons. Comparison 1, comparison 2. And then we can know these 3 line segments, whether they are parallel or not. Or we can determine how strong the interaction will be on the left part. Similar, on the right part, we have another 2 comparisons. Therefore, there will be total 4 comparisons to determine how strong the interaction will be in 3-level control factors. So in the other way, means that there will be 4 degrees of freedom. And by applying the previous formula, we can see 3 minus 1 multiplied by 3 minus 1 will be 4. So the 3-level interaction, the degree of freedom will be 4. Okay, any questions? All right, so here, 2 degree of freedom, 2 degree of freedom, so total 4 degree of freedom. So how to calculate the total number of degree of freedom, or how to calculate what is the total unknown variables in your model? We can calculate the total degree of freedom. This will be one example. If you have an experiment, you have 6 3-level factors. A, B, C, D, E, F are all 3-level. And you only need to consider one interaction, A, B. And the rest of the interaction are negligible, very small. You don't need to consider. So you only need to consider 6 main effects and 1 interaction. Now I want you to calculate what is the total number of degree of freedom using the similar we just introduced before. This is additive model, right? And the additive model will become this main effect plus 1 interaction effect. Okay, and this main effect, we have 1, 2, 3, 4, 5, 6 3-level, so 12 degree of freedom. How about this interaction AB? Because they are 3-level, so there will be 4 degree of freedom, which means that in our model, there will be total 12 plus 4, 16 unknown variables, or actually there will be another one, mu. But usually the degree of freedom, we automatically deduct 1 for the mean. So which means that we need the total degree of freedom will be 16. 16. All right. If you know that the total degree of freedom will be 16, which means that you need at least 17 samples, which will give you 17 equations. Therefore, you can solve all these unknown variables, okay, from mathematical way. So from here, you can see in your orthogonal array, need to have at least have 16 plus 1, 17 samples in order to solve all the result, not to consider possible interaction, right? Not, I'm sorry, possible confounding, but at least you need to have 17 design. You need to select an orthogonal array larger than 17. So for each orthogonal array, what is the total degree of freedom? If your orthogonal array is Ln, and we usually will deduct 1 degree of freedom for the average, so this can only solve for n minus 1 unknown variables, main effects and interactions. So when you come up a design from the calculation of degree of freedom, you can have an estimate how big our orthogonal array has to be in order to solve all the unknown variables, right? So here, L8, you have 7 degree of freedom, right? For the orthogonal array, where are those 7 degree of freedom? Because you have 7 columns. Each column can be arranged for 2-level factors, which means that you are allowed to put 7 control factors in this orthogonal array. Each control factors are 2-level, which will be 1 degree of freedom. Therefore, 1, 2, 3, 4, 5, 6, 7. This L8 orthogonal array will have 7 degree of freedom, since you can arrange your control factor here. Similar, if you look at L9, right? L9 have 9 experiments, but L9 only have 4 columns. Why you only have 4 columns? Why doesn't it have 6, 5, 6, 7 more columns? Because for each columns, they can be arranged for 3-level factors. Therefore, each columns will need 2 degree of freedom. Right? If you put a factor, 3-level factor here, this will need 2 degree of freedom. And you have 4 columns, 2, 2, 2, 2. 8 degree of freedom. Because you only have L9, the total degree of freedom are 8. That is the reason why in L9 orthogonal array only have 4 columns instead of more columns, because it uses all the degree of freedom already. So there are some more examples following like that. For instance, you want to compare whether this selection of orthogonal array is reasonable or not. So from here you can see if you have 2 level, but 1 2 level, 5 3 level, 1 interaction AB, and for the rest of the interaction are negligible. What is the total degree of freedom? By using what we told you before, A 2 level, so the degree of freedom will be 1. 3 level, 5, 3 level, so 5, 2 degree of freedom, and 1 interaction AB. AB, A is 2 level, B is 3 level. So AB here, the interaction effect will be 2 degree of freedom, right? Now this is DOF for the interaction term. Therefore, the total degree of freedom will be 13. Will be a 13. And your experiment has to be more than 14 experiments. You have to be more than 14 samples, 14 experiments in your orthogonal array in order to estimate all the effects, main effects and the interaction effects. So this is what it said. OA has to be larger than the required degree of freedom. And you have to make sure that the level is consistent. 2 level in 2 level column, 3 level in 3 level columns, right? Okay, let's stop here. Any questions? Then we can start to, let's use the Excel to explain how to do the first decomposition for control factors. Okay, so please open the Excel file. I give you in the 教学平台. Okay, 好，该起来了哈。So please open the data. Any problem? Did you know where to get this data file? All right. Let's try to calculate what is the degree of freedom and sum of square for A, B, C, D. Okay? If you did that before, you should know what is the process. The first steps are similar to what we did before. We need to do analysis of variance, try to find out the response table for A, B, C, D, E, okay? So let's try to find out what is the response table, and next we want to find out what is the main effect. Should be very straightforward. I will show you again. All right, and this is the total average. Only for as a check to see if they are correct. If they are the same, 16.72, these two are the same, which means that you are okay, right? We're using this one as a correctness check. You can follow a similar way to finish all the response table. Once you finish the response table, you will be able to find out the main effect for A1, A2. Here, the main effect of A1 will be equal to the average output minus the total average. Total average, let's put it here. Okay, let's make it here or there. Okay, and let's fix it easier. Let's fix it, all right? So this is the, all right, A1, same thing, A2. You can do the same thing for A, B, C, D, E, then you can get all the main effects. I believe this should be the answer you get. Okay, this is what we did before the midterm, should be no problem. Practice makes perfect. So although this is very say, repetitive. But I still want you to do this practice. So you will be able to find out the many facts. Okay, I believe some of you should have finished that. Okay, good. Okay. Now let's try to calculate the sum of square and degree of freedom for the many facts. We will talk about interaction next time. So the table was looked like this one, but now we only consider A, B, C, D, E, and let's say neglect that for now. And we'll talk about interaction later. So let's calculate what is the degree of freedom. Should be very straightforward. How about total degree of freedom? What is the total degree of freedom? We are using L8. So these samples have 8 experiments or 8 combinations. Therefore, the degree of freedom will be n minus 1, 8 minus 1. So the total degree of freedom will be 7. Okay, how about sum of square? Sum of square are very straightforward. As we talked about before, this is the sum of square for the many fact A1, A2, multiplied by the number of repetition in the total orthogonal array. This is L8 orthogonal array. So A1 will have 4 times, A2 will have 4 times. So we just need to calculate how to calculate sum of square due to A will be the summation of A1, A2, sum of square A1, A2 multiplied by 4. Just like the PPT. The sum of square due to A will be A1 squared plus A2 squared, and each will repeat 4 times in the L8, right? 8 experiment, 4 times, 4 times. So 4 A1 squared, 4 A2 squared. Then, it's very straightforward. Sum of square due to A will be equal to, we can use sum of square, SUM square. This is the function in Excel. It will automatically return the sum of square. Here, we want to calculate sum square for A. So A1, A2, these two. So we just need to select A1, A2. A1, A2. Right quote. And we need to multiply by number of repetition in L8. Each level will repeat 4 times. So you can multiply 4. So you can get a sum square for A. And result will be 220. Oh, sorry. I selected the wrong one. Not this one. This is not main fair. This is response table. I should select here. These two. Sorry, these two. So the sum square will be 0.08. And you can compare that with your lecture notes. You'll find out the number are the same. We can make it a little bit, have more decimals, so it will be easier to compare. 0.080. This sum square due to A. Same thing, sum square due to B. B1, B2. Not this one. That is response table. We are summation the many fact. Okay, you need to set this one. Many fact. Here. And again, it will be 4 times for each label multiplied by 4. If you are using 3 label, L9, they will be different. Do the same thing. Okay, then you can calculate sum of square for A, B, C, D, E. Any questions? Now, you want to calculate what is the total sum of square. Total sum square, let's go back to the PPT. How to calculate the total sum of square? Here, the total sum of square, Okay, the final, okay, this can be decomposed these two, but the calculation can be simplified into the summation of all the experimental output, sum square for all the experimental output, minus total number of experiment, and multiplied by average square. All right, there are some mathematical process. I simplified that. I didn't show you here, but basically all the interaction terms will be canceled out again. Okay, if you finish this process, you can find out this can be simplified into that. Therefore, how to get the total sum square in the ANOVA table. Let's go back here. This one will be equal to sum of square for all the output here, all the output. Right? Minus the number of experiment, 8, multiplied by the average square, the total average square. Enter, you get the result will be 28.708. This is this one, right? Total sum square for all the output minus number of experiment multiplied by the average square. So far, so good? All right. How about this one? What is the sum square for error? What is the degree of freedom for error? Here, let's show you this PPT. So how to get the adaptive model, and already show you here. This is how we get it, right? This is a summation of the previous result. And there are two properties in ANOVA. First property is the total sum square for in ANOVA, which means that the total sum square is the sum square due to main effect and the sum square due to error. Remember, this TSS can be equal to pi because we move this term to the left. On the right hand, we have sum square due to main effect and sum square due to error. So we can use this equation. How to calculate sum square due to error? Basically, we subtract main effect from the total sum square. Move this here. You can find out the sum square due to error. Any questions? All right. So here, go back to the Excel. What is the total sum square due to error? This will be equal to the total sum square here, minus sum square due to main effect. This sum square due to main effect. Okay? Here, total sum square minus the sum square due to main effect A, B, C, D, E. The rest will be sum square due to error, 0.0752. Any questions? Then how about the degree of freedom? The same. Another property in ANOVA is the decompose for degree of freedom. In our experiment, the total degree of freedom will be the number of experiment minus 1. And you use sum of a degree of freedom to estimate the main effect. So the rest of the degree of freedom can be used to estimate the sum of square due to error. So the degree of freedom for sum of square for the error terms will be here. Degree of freedom due to error will be total degree of freedom, which is n minus 1. In L8 will be 7 minus 1. 8 minus 1 will be 7. Minus how many degree of freedom you are used to estimate the main effects. In our case, 5, right? So let's go back to the Excel table. How many degree of freedom can be used to estimate the main effect? I'm sorry, the error. Here, total degree of freedom is 7. And we are using 1, 2, 3, 4, 5 degree of freedom to estimate the main effects. Therefore, you will have 2 degree of freedom, 7 minus 5 to estimate the error terms, or the difference are due to the change of the error terms. So here, the degree of freedom for error will be equal to total sum square degree of freedom minus the degree of freedom for your model. Here you have 5 two-level in your model, so your degree of freedom for error in this case will be 2 degree of freedom. Any questions?